WarsawJS.
Hello. So I was thinking how to start this presentation, but my eyes got sort of not wet. I forgot my eye drops. Did you know that actually eyes is the only part of the body that gets oxygen through air and not like blood system? Anyway, we're going to talk about distributed systems for front-end engineers. I think that understanding backend and understanding distributed systems will make you better front-end engineers. So who am I? My name is Sasha. I work on distributed systems at Box. My team in particular does distributed messaging. We are providing best-in-class point-to-point delivery systems, scheduled and repeated jobs, and we also allow our engineers to effortlessly benefit from publish-subscribe communication. So actually, I used to be a front-end engineer. That's why I came here to share with you and try to convince you to move to the dark side, simply because it's much cooler, it's also less stressful, and you can sort of enjoy it more. Now, our journey today will begin with an exploration of what actually happens once you click a button to stuff appearing on your screen. We will take a social network as an example, and we will learn all the concepts taken into account this example. So we will scale it from absolutely nothing to a large distributed system. We will select a data storage for it. We will learn about communication patterns and technique, and we will ensure that our system is reliable. Now, what actually happens? So we click a button, voila, your backend returns JSON, like you're happy. You call some Axios on the front-end side, underneath is an HTTP request. You don't really care what's going on, right? Well, wrong. So to make sure that we have the same foundation, HTTP is a client-server protocol that makes sure that our messages get delivered and that we get a response. This will be important later on when we discuss protocols for the backend. Well, underneath, it's not as simple when you click a button. This is not a real system, by the way, so don't copy it, don't repeat it at home, really. I drew it in like 5 minutes. So once your request reaches the so-called backend, it goes to an authorization service, then it goes to a microservice that may be calling 5 other services. It may have cache, may have their own database, may produce 5 different events. It is also auto-scalable, rate limited, and so on. So this escalated sort of quickly. As you see, we cannot really understand what's going on. Let's start from the beginning. A distributed system can be defined as a set of computers connected through a network that work as a single computer. So let's talk about this in the context of a social network. Let's say we build our new Facebook, whatever. We push our code on our local computer. We connect it to some MySQL. We map our local home IP address to some GoDaddy domain name, and it's done, actually, it works. Now, we have no users, so one computer is actually not a problem. That's what I would do, actually. As we get more users, we would need more computers. Now, here's where the problem starts. Once we have 1 or more computers, you need a load balancer to distribute the traffic between those. So we will have a load balancer that directs the traffic either to one instance or to another. And we'll also extract our MySQL to a separate computer to make sure the data is consistent. As we scale further, we have more users, more traffic. There is actually very little difference between 2 computers and n computers. So we may just add more computers, and that would be it. Most of the companies can and should stop here, simply because they don't need further expansion into the field of microservices. Companies like Box need to scale further, simply because our system is so big and so complex. The amount of users simply, well, it's kind of hard to handle when you have a monolith. So once you have a monolith and your company is big enough, you have suddenly authorization teams breaking photo storage, you have problems like infrastructure, trying to max out your database's performance. It gets difficult pretty quickly, and I worked at such company. Now, That's why we are moving to microservices. So what do? We move functional specific components to a separate executable node. And yeah, that's it. The term micro doesn't necessarily mean small. It means smaller. This is very important since a lot of people think that, okay, microservice is like, that's only one thing. No, it can do a lot of stuff. We also extract our database. Oh, sorry. Yeah, each microservice will have their own database simply because this allows us to avoid a mess. If you have two microservices accessing the same database, then you won't know where is the change happening, and also you will have race condition and other kinds of problems. Doesn't make it clear so far? Is it good? Good? Do you understand what we do on the backend? Good. However, it comes with a lot of problems. Once we extract it, once we have each database for each service, how do we synchronize data between the microservices, right? It's kind of a mess. And if you do synchronize them, then there is also latency between the computers. So what do? That's where CAP theorem comes in. So developed by Eric Buer many years ago, it says that we cannot provide 100% guarantees for the following constraints. We have consistency, partition tolerance, and availability. So a little bit about that. Consistency is when on every read operation, we return the newest data. Availability is when we return non-error response without a delay on every request. And partition tolerance is when our system is available, even if some nodes are down. This still is a bit complicated. Actually, I didn't get it for the first time and second. So there is an updated version of CAP, which is much simpler. We either sacrifice consistency or latency. Now, what happened with partition tolerance? It's pretty simple. In modern world, the system is either partition tolerant or not. So we don't care about that. Most distributed systems are partition tolerant, and if your system is not, then you should hire better engineers. Now, taking into account CAP, we should think, how do we select our data storage? We have mainly two types on the backend, SQL and NoSQL. Well, each comes with each pros and cons. SQL is good when you have relationships. So whenever you have some sort of relationships, it's good to choose. However, it has high consistency, but really bad at latency. So whenever you try to scale out SQL, there's a problem starts. When it comes to NoSQL, we don't have any structure most of the time. We have high scalability simply because such database was designed for high load. However, it comes for a specific use case. For example, we have NoSQL databases for key value, for JSON objects, geographical locations, we have time series, and all kinds of stuff. They were created for a single purpose of handling an enormous load for a specific use case. Oh, they also don't guarantee consistency. Yeah. Now, it doesn't matter whether, oh, sorry, what is going on? So we have two ways of communicating between microservices. Since we now know the data storages, we store the data. However, they need to talk to each other. We have two ways, synchronous or asynchronous. So asynchronous communication is the one that you are familiar with. This is HTTP and TCP. You send a request, you wait for the response, you get your response. It causes blocking behavior. However, the big pros of it is that both client and server are synchronized. Asynchronous is when you kind of like in the real world example, you will send a postcard to your friend in Japan and it just works. Well, your friend will pick it up from the postal office when he is available. So we don't have any blocking behavior. This allows us to have higher performance. However, it comes with the sacrifice of requiring more logic to handle errors and responses. Now, it doesn't matter whether we use synchronous or asynchronous communication. We need to transfer data somehow. We need some data standard, right? So here we have a simple example of a JSON. Just 3 fields, name, age, and email. And we're going to try to transfer it on the backend. We have many protocols on the backend. The ones that you're familiar with are JSONs over HTTP. You may know JSON over TCP. However, they're not really optimal for the backend simply because we don't need a lot of stuff. So JSON in UTF-8 payload costs us 64 bytes, while Avro and protobuf comes in 50 and 30. And as you see, most of the stuff is taken by HTTP headers, which we really don't need. So we can just throw it away. So you say, okay, 300 bytes versus 70, not that big of a difference, right? Oh, wrong. It's just 3 simple fields, and imagine we have 1 million such messages per second, which is not a lot. This will come at a cost of 26 terabytes versus just 6 in a year. And this is just a small piece of data, unrealistic example. In the real world, we have much bigger ones. So we need to think about that on the backend too. Now, ensuring systems reliability is quite important. Because we're a social network, we basically earn money on ads. Every second we're down, we can lose millions of dollars. So that's pretty bad. So how do we make sure it doesn't happen? Well, we have redundancies. So we have more than we need to. We have more instances of execution nodes, more database instances, and so on. This will allow us to redirect traffic to healthy instances. Load balancers play a crucial role for it, simply because they handle failovers and make sure that the traffic goes to healthy instances only. Now, monitoring and observability, probably one of my favorite topics. I cannot stress this enough on how important it is, especially coming from the front-end side, because you basically see your outcome, whether it works or not. Well, on the backend, you don't. So we collect metrics, logs, traces, everything we can. So in case we have a problem, we look at our observability instead of guessing. On the backend, we are simply blind if we don't have it. Now, we may have redundancies and proper observability. However, we will still fail from time to time. That's why people like me are still employed. So, yeah, what? Yeah, thanks. So we can implement different resilience patterns, such as retries or cascading failures prevention or timeouts. All of that will help us. However, also a big one would be diversifying through geography. For example, we started with, as you remember, just one computer. Well, what if it burns down? Well, we can have 2 computers. What if our apartments burns down where those computers are? We can have multiple apartments. We can have multiple cities if a hurricane comes in. We can spread out through different regions, countries, and even continents. It's just a question of how far do we want to go. And I came a little bit faster than I was supposed to, since I usually talk fast. So as a conclusion, we sort of now, I hope, understand better what we as backend engineers do and what distributed systems people do. We know how to scale application from 0 to n, and we know that microservices is not just a flashy term, but rather a necessity for a lot of companies. We know how CAP theorem applies to real-world choices, and we know the difference between SQL and MySQL databases for specific use cases, difference between synchronous and asynchronous communication protocols and how they affect our performance and bandwidth. And we, of course, understand the redundancy and monitoring. And thank you for your attention. If you have any question, I will be happy to answer them.
Thank you very much. Thank you very much. Any questions for Sasha?
Hi, I got a question, like regarding, you showed on one of the pictures that you split your database from one instance to several instances. Oh, very in the beginning. Okay, what strategies do you use in like splitting the database?
Oh, no.
Let's say 2 microservices use the user entity.
Yeah, so in the real world, how it happens is that you have a second, you basically copy your database, and there is a whole algorithm on how you do it. You replicate your database as in the, well, databases allow you to save the log on all of the changes. So what you do is you take that log and you replicate the exact state of the database. Then you write to both databases, you fill the gap, you also fill the gap after that, and then you cut off the old one. Does it make sense? Like there is basically on the internet a whole algorithm for that.
It sounds like you need a diagram for that.
Wow. Yeah, this is true.
Any other questions? for Sasha.
So you mentioned that headers for JSON, sorry, Sasha, headers can be redundant information. So what if in the JSON we also have long field names? Is there a common practice for backend communication to like name fields A, B, C and just decode them on the other side to save the payload size?
So that's what Avro and Protobuf does actually. Yeah, simple as that. They save a lot of space. We also have. Are you okay? We also have a concept
Whoa,
of.
bravo!
So on the backend, we also have a concept of headers if we need it. And what we do is that Avro and Protobuf does exactly what you said. They can sort of just have fields number 1, number 2, number 3. That saves a lot of space for us.
All right, thank you.
Very immediate answers. It seems like you're prepared for any eventuality. I like this idea of redundancy. For me, that was the resounding message that stuck with me. Anyone else? Question?
Yeah.
For Sasha? Where?
So when should we scale database horizontally? I see that your feed.
Okay, I see.
I see that your feed service, microservice, have just one database. When should we have multiple instances for? If you have like multiple feed services, probably database will be bottleneck. So when should we scale database?
Okay, I don't understand the question. Sorry.
I mean, okay. Imagine you have multiple feed services, like tons of them, and you can have one instance of database.
Yep.
You may need to have like multiple instances of the same database.
Yep.
When and how should we scale it?
The database?
Yeah.
Well, whenever you need to. So it depends on your tech stack. If you're using something like GCP or AWS, then it will scale out for you.
Vertically or horizontally?
I think it depends on the type of database you use.
I think if you have like, it's not easy to synchronize even databases.
Yeah, it's not. Yeah, I'm not saying it is. So that's why I said that SQL databases are really bad. Did I say it? At scaling out. At max, you can have something called master-slave architecture or main and follower. And what else? There's also a few tricks, but that's all you can do, really.
Main and follower, I like that.
Yeah.
I think we discussed this language of master and slave earlier at another meeting.
Yeah, sorry.
It's quite all right.
Okay. Sorry, why NoSQL databases are so good at scaling out?
Well, they were designed for that. Like companies like Facebook actually came up into one room and said that, okay, we need some databases that need to handle our use cases because we have a lot of traffic. So the database like Cassandra was designed like that to handle enormous load. But architecture of Cassandra is really complex, so it needs a whole presentation on its own and probably a few scientific papers.
But okay, we still have MongoDB. It's still NoSQL database, and that, I don't think that it is such good at scaling out.
Sorry, again?
Is MongoDB good at scaling out? It's still NoSQL database, but I think that...
I never used it in production, so I don't know.
Hi. So have you heard about this anti-pattern called distributed monolith?
Of course.
Can you tell me something about it, like how to avoid it or what
Yeah,
leads to it? Thanks.
So, from my perspective, we should hire good engineers at first. No, really, like, I've seen a lot of mistakes done simply because of over-engineering or people not really understanding what they're doing. So that would be the first thing that comes to my mind. I would say that one team should own a particular microservice. You don't spread out it through different teams, and a microservice should serve only its purpose. For example, authorization does authorization, emailing service does emailing, and nothing else. And yeah, this is pretty much it.
Yeah. How to avoid this monolith situation. It sounds like very wise advice. It sounds like, have you ever faced that situation yourself personally?
Distributed monolith?
Yeah.
No, but I got lucky with getting into good companies.
I guess I think the advice of hiring good engineers was great. Listen, folks, that's the end of Sasha's presentation. Please give him a really, really big round of applause.
Thank you.